This is Dr. Carroll. This is another video about graph exercises. So let's keep going. When we have an adjacency matrix representation, most graphs are going to require a big omega v squared, but there are some exceptions. And to be clear here, big omega means that's the minimum time required, different from big O. So let's show that determining whether a directed graph G has a universal sink, meaning there's a vertex with an in-degree from every other vertex and an out degree of 0. So a sink meaning everything goes into it, nothing's coming out. And let's see if that can be determined in big O of V time, given an adjacency matrix for G. So some important things to establish to help us understand this is, first, there's at most one sink per G. So let's go through a high level of how we do this, and let's go through some pseudocode, and then let's see it executed. So first, we're just going to assume every vertex is the universal sink, and we're going to track this with a variable s. And then we're going to iteratively choose two vertices that could be the sink, and then check the edge between them. If there's not an edge, so a 0 in an adjacency matrix, then the two vertex cannot be the sink, because we know that there isn't an edge going to that vertex. Otherwise, if there is an edge, that means the from vertex cannot be the sink. So notice how clever that is. With picking one edge, we can eliminate one of the two vertices to determine which one it could be. And so then we'll apply this over and over again very strategically to go through the vertices, eliminating one each iteration. Then for the single remaining sink, if there is any, we verify that it has an in-degree that would allow it to be the universal sink. Great. Okay, so let's look at some pseudocode. So I mentioned we'll be tracking the potential universal sinks with S. So let's set S sub I to 1, meaning that they could be a potential sink, and do that for all indices starting at 1 and going up to the size of V. And so that's our possible sinks. Now we have an F and T variables to track from and to. So we'll initialize from to be the first one. In this case, we're starting with 1. That's our from vertex. And then T for our to vertex. We're going to start at the next one. Then we're going to start with the, we're going to go through an iteration for each vertex, but we can start at 2 because we're considering pairs. So then we test to look in our adjacency matrix here, represented by A, from 2 vertices, and if it's 0, then that means the 2 vertex does not have an edge from F. So T, the vertex that has the same indice as T, cannot be the sink. And so it can't be the sink. We're going to mark that in our S array to 0, and then we're going to increment it to 1 more, to the next possible one. But there's the other condition. What if there is an edge from F to T? That means the T vertex, we have the T vertex does have an edge from F, so F cannot be the sink. So then we'll update that F can't be the sink, and we'll change what vertex it's pointing to. Now now we have the end game here. So now we test to figure out which one did we leave off with. So we're going to look at the result of that last if test. And so if T is less than the size of V, well then that's our potential source. Otherwise, it's the from one. And then we need to verify that our potential source has the right in degree, that all other vertices are coming to it. So we'll keep track of that, the in degree of S. We're going to walk through every vertex, adding them up. And this is just binary, and whether they're there or not. And so we're expecting that if it's a universal sink, the in degree will be the size of the set of vertices minus 1. But we also need to check, notice how we just went from 1 to V, that it doesn't have a circular edge, a self edge to the potential sink. And so we'll need to check for that as well. From S to S, we need to make sure that that doesn't disqualify it. If it passes both those tests, we have it, a universal sink. Otherwise, we could return something like -1. Okay, I produced this random adjacency matrix here, and then now let's go through it. I probably tweaked it a little bit. And so here I have my S array set up. I've already initialized it all to 1. I've already set F to 1 and T to 2, representing A and B here. And so let's go through this. Let's see, we've done these first couple. Now we're going to see in the adjacency matrix from A to B, is it a 1 or a 0? And it is a 0. So that means we can set that B cannot be the universal sink. And so we're going to consider now C as in the 2 position. Now let's repeat. Now we're looking at A to C. Oh, there is an edge from A to C. So then that disqualifies vertex A. We're going to update the S array for that. And then we need to update our from index here. Now we're from D to C. There isn't an edge there. So that means C can't be a universal sink. And so then we're going to update T. Notice we're going to hop over F because we don't need to look at from D to D. We're going to say from D to E. So from D to E, and oh, there's no edge there, so that means E can't be the universal sink. We'll update that, increment T. Now we're looking from D to F. There's not an edge there, so we'll update update the potential for F to be a universal sink and update T. Now we're done with the loop. Now we're going to test to see which one, the from or the to, is our potential sink. We see that T isn't referencing a valid index, so then we're going to assign S to B to F. Then we're going to go through from D and add up all of, no, I'm sorry. We're going to do 2D. We're going to add up all of the values in the column that are going to D, to our potential source. Add those up, and sure enough, we're going to see that there's 1 in each of those except 1 from itself, and so then that's going to pass this last test, and so we're going to say that D is the universal sink. Now let's change this up just a little bit. Let's back up just a little bit here. Oh, I can go a little bit further. Okay, what if we said that there was an edge here? Okay, let's change it. There was an edge here. So we can see D can no longer be the universal sink. Let's just see what happens. We have from D to F. There's a 1 there, so we say, oh, D cannot be the universal sink. So then we update F to be 1 more than where we were, and that concludes our iteration through. And so then we say, well, the potential sink is F here. It's the only one that's left. So then we would add up all of the values in the 2F column, and notice that it's 2, which is not the size of the vertices. We don't have an in degree from everyone except ourselves, and so it fails that, so it would return -1 instead. And so that would be our source. Let's do another one. Let's list the vertices in the order that a depth first search and a breadth first search would visit based on this graph, starting at A. And I'm going to arbitrarily always choose the nodes in alphabetical order, but it's really just going to depend on the algorithm for what the order will actually be when we have more than one choice. So let's go through this. So we're going to start at A. We're doing a depth first search, and so depth first search is going to go down, 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 down as fast as possible. So I have 3 choices here, B, C, or F. I'm going to arbitrarily choose B because of alphabetical order. And so now we're at B. We're going to keep going for depth first, so we can go to C, to D, or F. So I'm going to arbitrarily choose C because of alphabetical order. Now from C, we only have one choice, and that's E. So we're going to take it. From E, we only have one choice, D. Now D, we've already been, only has one choice, and that's 2C, and we've already been there, so we're going to backtrack. We're going to backtrack to E and see that it doesn't have any other choices still. We're going to backtrack to C and see that we've exhausted all of its choices. We're going to backtrack to B and see that sure enough B can get to F, so we go from B to F, and that's going to be our depth first search traversal. Now another common search is breadth first search. I like to think of exploring in levels, 1 level away from the original point, and then 2 levels, and then 3 levels. So we're going to start at A, and our first level is going to include B, C, and F. Notice it includes F because we can get from F to A. Now we're going to do all of the vertices that are adjacent to B, C, and F. Well, we can get from B to C, but we've already explored C, so we're not going to do that one again. So this would include D from B, that is, and E from C. And so there we have our breadth first search. Now let's talk about what is the runtime for a breadth first search in terms of our sets of edges and our sets of vertices. So the first question is, are we talking about adjacency list or adjacency matrix? Let's tackle adjacency list first. Well, the short answer is we're going to end up with the big O of this proportional to the size of the set of vertices plus the size of edges. Let's work through that. In the worst case, let's see, what would be the worst case for this? The worst case would be for a connected graph. We can get to every single vertex, and we're going to end up visiting every vertex that's a member of V and every edge. And so, but we're not going to do more than that, and so that's how we get V plus E. Now let's talk about adjacency matrix. This is going to be V squared, and that's probably not surprising because of how it's set up. We don't know which edges exist or not until we test them, and we're at a matrix, so we have to go through and see which ones are present or not. So in the worst case for a connected graph, we're going to end up looping at every possible edge from every vertex. We're going to be doing a lot of backtracking, but we're not going to do more than that. And so we're going to look at every possibility for each edge, whether it's there or not. And so since it's stored in a matrix, we're going to, and the size of the matrix it's a square matrix, it's V, then we're going to have V squared. What's interesting for depth first search is we have the exact same big O's for depth first search. Isn't that interesting? Well, thanks for watching this video. Check out my other videos.